Hello friends, and welcome to our new science journey. Imagine a world so vast it could swallow 1,000 Earths, yet it spins a full day in less than your night's sleep. Picture storms older than nations, lightning blooming beneath towers of ice and vapor, and a hidden furnace that outshines the sunlight it receives. Rings made of dust, moons that pull oceans under ice, a magnetic realm that sculpts space itself. This is not fantasy, it's waiting above us. Stay close, we'll reveal its quiet power, layer by patient layer. Jupiter breathes quietly in the dark, an enormous world that does not sleep. Its presence steadies the outer system, a slow anchor in the sun's wide reach. The planet is ancient by our calendars, formed from gas and ice captured early in the solar system's unsettled youth. Astronomers trace that beginning in the protoplanetary disk, where pebbles became boulders, and a rocky kernel gained enough mass to gather hydrogen and helium. That gathering did not stop at modest amounts. It swept a vast domain. Jupiter's mass ended at more than 300 times Earth's, yet it remains mostly gas above pressures that crush chemistry into new phases. The planet does not shine like the sun, but it does not only reflect light either. It radiates heat from within, energy left from formation, and from processes still unfolding under its cloud tops. Probes and telescopes have measured this extra glow and found it steady, as if the planet keeps a banked ember behind its weather. Cloud bands ring the globe. They are not painted stripes, but moving belts and zones with winds that race in opposite directions. Ammonia, water, and other compounds condense in these skies, forming layered clouds whose colors tell stories of chemistry and depth. There are storms the size of continents that last longer than empires, and small tempests that bloom and fade in a single season. The magnetic field is immense, trapping charged particles in rings of radiation. It hums with interactions from volcanic moons and the solar wind. Around this world, faint rings drift, and dozens of moons keep time in graceful gravitational patterns. Picture it for a moment. A lighthouse made of pressure and spin, turning without pause. Then let the image pass, and the facts remain. Jupiter's pull influences more than its immediate neighborhood. It sculpts gaps in the asteroid belt and shepherds swarms of co-orbiting asteroids ahead of and behind its path. It is not a shield, not exactly, but a referee of orbits, redirecting ice and stone with every century. Settle into this quiet. Let the distances stretch and the numbers soften at the edges. We will move through steady truths, cloud to core, field to moon without hurry. If sleep comes, let it come as gently as a shadow, crossing a calm sea. If your breathing slowed, let the signal travel like, share, and subscribe, and guide another wanderer to the shoreline of sleep. Hundreds of Earths gathered into one globe, yet it never crossed the quiet threshold that would have lit fusion. The material gathered early from the young sun's disk, when icy grains and rocky seeds collided until gravity did the rest. Hydrogen and helium dominate from top to deep interior, the same elements that make stars burn, but here they remain bound as fluid, compressed by pressure instead of fired by heat. The planet spans a mean radius close to 11 times Earth's, which turns familiar scales into small suggestions beside it. There is no solid ground to walk upon. What observers call the cloud top is defined by pressure, not rock, close to the level we breathe at sea, and everything below grows heavier and hotter. Temperatures rise with depth into ranges where chemistry alters, and hydrogen changes its manners under force. The pull at the visible level exceeds what our bodies know by a comfortable margin, strong enough to hold even the lightest molecules for ages far exceeding human memory. That grip, combined with the planet's size, has quietly shaped the solar system's architecture. Gravitational tugs repeated over countless circuits, cleared orbital niches, sculpted patterns in the asteroid belt, and encouraged icy travelers to new, often shorter paths toward the Sunday. Formation models depend on this giant's early arrival. Because a growing world, this massive influences what can assemble inside its orbit. That influence continues now, evident in resonances that steer minor bodies into rhythms of avoidance or encounter. The atmosphere above the deeper layers holds more than hydrogen and helium. Trace gases, ammonia, methane, and water vapor. Among them offer markers that vary by height and latitude. Instruments track these fingerprints to judge circulation, cloud heights, and mixing. Sunlight paints the upper layers by reflection, but the planet adds its own heat from within, energy left over from its birth, and released slowly as gravity continues to rearrange the interior. The result is a gentle infrared glow that instruments detect even on the night side. Beneath the clouds, gas compresses as depth increases and density climbs. Electrons in hydrogen's atoms begin to share crowded space in ways unfamiliar on a calm Earth day, shifting the fluid toward behaviors that conduct and respond to magnetic forces. The core, if it survives as a neat boundary, likely does not resemble a mountain. It is a region rich in heavy elements, possibly diluted, merging into surrounding layers without a sharp edge. What matters to our quiet hour is not the jargon, but the assurance that structure underlies the cloud show, ordered by pressure and temperature rather than land. The giant's presence has always been dependable. Observatories track it across decades and find constancy in large traits, even as small markings evolve. That steadiness mirrors a truth close to home. Weight can become guidance. A heavy friend at a crowded crossing does not shout. They simply stand where movement is safest and the crowd shapes around them. The planet's gravity has done something similar on a cosmic scale, not as a shield, but as a calm organizer of traffic. If you step outside on a clear night and seek a bright point misted by our air, the light you see has bounced from high clouds where pressure changes with altitude rather than land. That knowledge does not demand action. It invites a slower breath. Mass here is not punishment or drama. It is order held without E between them, because when matter collects on this scale, it does not rest, it turns. Inward from the ammonia, ice, and water vapor, deeper than the layers that paint ochres and creams, the gas thickens. Equations of state sharpen our view of these depths, testing in laboratories how hydrogen behaves under crushing force, then comparing the results with spacecraft measurements of gravity and rotation to map how density must be arranged. The picture is not finished, but it is not a guess. Data constrain the shape, the distribution of heavy elements, and the thickness of layers where electrons begin to flow more freely. From such details we gain a different comfort, ignorance shrinking around the edges while mystery remains at the core, patient, not hostile. In the wider neighborhood, Jupiter's mass defines the so-called Hill sphere, a domain where its gravity outcompetes the Sun's for custody of small bodies. That domain holds dozens upon dozens of moons with varied paths and histories. Some likely formed from the planet's circumplanetary disk. Others were captured and settled into paths that now seem natural. Rings of dust orbit within, pale and persistent, replenished by tiny impacts. Even Trojan companions travel ahead of and behind the planet along its solar path, evidence that mass can herd without touching. Each of these features belongs to mass applied over time, not as a sprint but as a natural state. Feel how that idea threads quietly into a human evening. When the day has asked much, the body has weight, and that weight can become an anchor rather than a burden. In the same way, Jupiter's gathered material has anchored patterns that might otherwise have scattered. No one thanks it. It does not need thanks. It turns in its lane and keeps the beat of its orbit. As quiet as the thought that arrives before sleep, it influences without noise and shows that weight, carried well, calms the room. And so the mind can move from size to motion without any sharp, edgy. The shortest day expands here. A world this wide completes a full spin in less than 10 hours, and that rhythm defines the mood of the entire atmosphere. The rotation reshapes the planet's figure, narrowing the distance pole to pole and broadening along the equator. Images show the difference clearly, and careful measurements trace how far the equatorial radius exceeds the polar one. The reason is simple. Spin creates outward push, which competes with gravity most strongly where the world's surface sweeps fastest. The effect is not cosmetic. It changes how winds arrange themselves and how pressure surfaces tilt with latitude. Counting that short day is not as easy as watching a mark drift across the visible cloud tops because different bands slide at slightly different speeds. The atmosphere experiences differential rotation, with latitudes drifting relative to one another. To keep time, astronomers rely on the planet's deep engine, radio signals linked to the magnetic field, generated by motions far beneath the clouds, give a reference for rotation that does not shift with every storm or belt. Those emissions form a practical clock. They let observers compare decades of data without confusion when one jet strengthens and another weakens. Fast rotation does more than compress the day. It imprints order on the winds. The Coriolis effect, weak on a backyard scale, dominates here. Air parcels veer as they move, turning large north-south motions into east-west jets. The alternating direction of these jets, prograde, then retrograde, then prograde again, sets the bands that make the planet instantly recognizable. In a slower world, turbulence might smear such patterns. Here, rotation fences motions into lanes. The same spin influences depths we cannot see. Where hydrogen begins to conduct, layers are thought to rotate in columns parallel to the axis, a geometry encouraged by the lack of solid boundaries and the strength of planetary vorticity. That deep organization helps sustain the magnetic field, which stays aligned enough to define the radio clock, even as surface features drift. The short day also shapes thermal contrasts. Day and night pass quickly, so sunlight does not have time to build a strong daily cycle in temperatures at the cloud level. Instead, the planet's internal heat and the steady averaging effect of the fast spin keep conditions fairly even in longitude. Weather responds more to latitude, to the balance between rising zones and sinking belts, than to the hour of local dawn. The equator, sweeping fastest, experiences the greatest outward push, which helps explain the difference in shape and affects how deep isobars must sit to balance forces. This geometry supports strong equatorial jets and encourages waves that organize into long, repeating forms. The short day matters for everything charged or magnetic as well. Field lines that anchor to the atmosphere move through space quickly, sweeping past orbiting moons and their plasma trails. That motion accelerates particles and stretches the magnetic environment into structures that match the spin. The rapid turn also means any storm must negotiate a shifting frame. Even great vortices feel the rotation as a guiding hand, pushing their edges into curves and managing angular momentum like a quiet supervisor. For someone listening in a quiet room, the idea carries a human reflection. Sometimes life seems to demand longer days. Here, the brief day does not rush anything. It makes a rhythm that's dependable, like a heart, learning to slow after evening walks. Tasks find their lanes. Seconds do not shout. The world is large, yet it keeps time gently. Observers love that constancy. They can plan a glance at a feature and know when it will return. Over years, they watch the subtle drift of one band's speed compared with another, yet the underlying spin holds. The clock never forgets its beat. Think of a potter's wheel that turns quickly enough to steady hands. Clay that might wobble on a slow wheel settles into symmetry. In the same way, Jupiter's quick spin steadies patterns that would otherwise blur. Rotation also interacts with gravity to organize deeper flows. Centrifugal balance varies with latitude, and pressure surfaces adjust to keep total forces in step. This balance sets up thermal wind relationships that tie vertical shear of the jets to horizontal temperature gradients. Those gradients, although modest, are enough to matter. They give weather a spine. Without the fast spin, the atmosphere would look less banded, and long-lived structures might be rare. With it, eddies arrange along lanes and persist. A final, quiet note of reassurance runs with the short day. Even on a planet that sized itself beyond our familiar measures, time found a cadence that neither hurries nor drags. A single rotation finishes before an Earth workday might, but the feeling is not haste. It is repetition that soothes pattern over spectacle. As the evening deepens, the thought can carry you forward without a seam. Where spin holds the frame, the flows that fill it begin to show their lines. The first thing a small telescope shows is the striped face, alternating bright and dark arcs that circle the globe with careful symmetry. Those bands arise from organized winds that run roughly east-west, creating zones where air rises and belts where it sinks. In the pale zones, ammonia condenses at higher altitudes, making thicker, brighter clouds. In the darker belts, downwelling lowers the cloud tops, and warmer layers peek through with richer color. Between each pair lies a jet, some moving with the planet's rotation and the next moving against it. The pattern does not blur after a season. Many jets keep their character for years, though their exact speeds may wax and wane. Temperature differences between banded regions provide seeds for instabilities that spin up cyclones and anticyclones. These vortices pepper the boundaries, merge, and decay, yielding a dynamic texture that rides on top of the steady lanes. Vertical mixing lifts trace chemicals from deeper levels into sunlight, where they can tint clouds and leave signatures in spectra. Observations in the infrared reveal spots where clouds thin and deeper heat escapes more freely. These hot regions drift with the flow and can organize into sequences that look like a train of windows along a belt. Microwave instruments see further, finding that ammonia is not spread evenly. Instead, it varies with latitude and reaches in columns, revealing that the circulation penetrates beneath the highest clouds. Sunlight does not supply all the energy needed to maintain such activity. The planet's interior contributes heat that bubbles up without waiting for noon. With rapid rotation, the atmosphere favors long, zonal structures. Waves roll around the planet, sometimes manifesting as ripples in a zone's edge, sometimes as chevrons in a belt. These waves can interact with jets, trading momentum in ways that sharpen or blur boundaries. Some bands thin or thicken over the years, and occasionally a belt will fade as its underlying dynamics shift, only to reappear later. The system records both memory and change. Small storms can arise in clusters, their updrafts visible as bright cloud tops in certain wavelengths. When such clusters form near a jet's edge, shear can stretch them into streamers. Other times, flow convergence builds ovals that travel as coherent entities, like beads sliding along a string. The scale of these features varies from those smaller than continents to formations large enough to command attention in any image. Yet each is still tied to the grand scaffolding of the bands. The familiar pattern creates affection. Viewers learn the names of prominent belts and zones and watch them for news of change. Through this lens, the planet feels like a place where a person might return and find a known shoreline. That feeling serves sleep because recognition lowers the pulse. Even as the details shift, the basic map holds. Comparison with Earth helps the mind. Our planet's jet streams sweep west to east in mid-latitudes, with weather riding their edges, but they meander and break more freely on a sphere with continents and slower spin. Jupiter's lack of a solid surface and its faster rotation channel the motion into stronger, more frequent jets with cleaner boundaries. The outcome is a stratified atmosphere in motion, tied as much to latitude as to time of day. Deeper down, the zonal flows likely extend for thousands of kilometers, as indicated by subtle gravity measurements and the way the magnetic field couples to motion. That depth makes the bands more than paint. They are slices through a three-dimensional engine. Across the equator, a broad current runs, sometimes displaying wave patterns that hint at certain oscillations. Higher latitudes hold narrower jets and more frequent vortices, their lifetimes varying with local conditions and the buffet of waves from below. Over it all, the short day keeps the frame, gathering any attempt at meridional drift into curved motion. The emotional tone here is familiarity earned by long watching. One can leave the window and return after years to find the arrangement intact, though never frozen. It is like a favorite path whose pebbles change but whose turnings remain. And as the stripes hold attention, a persistent feature in one belt reminds us that banded order does not forbid singular longevity. It makes a stage for it. Without announcing a shift, the narration of wind and color moves the eye toward a southern latitude, where a storm has kept its seat beyond recorded centuries. In the southern tropics, a vast anticyclone circles with winds that can rival the swiftest currents nearby. Yet its core moves as a single, disciplined body. Telescopes from long ago sketched an oval there, and modern instruments confirm that the vortex has persisted, even as its outline has changed. Over the last human century, the dimensions have contracted, and the hue has wandered through rusts, corals, and occasional paleness. That color is not paint, it is chemistry shaped by sunlight and altitude. Materials drawn up from lower levels react under radiation near the top of the storm and settle into tones that shift with supply and height. The vortex lives between powerful jets, and it feeds on their shear. Smaller eddies approach and sometimes merge with it, donating spin and helping the larger structure maintain itself. At other times, the storm sheds material that drifts away along the belt, a fair exchange that keeps the balance. Its top rises above surrounding clouds, placing portions of it in different layers of light and chemistry than the lanes around it know. Instruments that sense temperature and aerosol depth show signatures consistent with elevated cloud tops and altered particle sizes. The vortex penetrates downward as well. Slight differences in the planet's gravity field measured during close passes imply a mass anomaly that extends below the highest visible deck, suggesting the storm's coherence reaches into levels where ammonia and water clouds mix with warmer air. Within the oval, a core region rotates more uniformly, while bands of flow around it manage the exchange with neighboring currents. The storm's perimeter is not a wall, but a shear layer, where velocities change across short distances, a place where filaments stretch and fold. These filaments twist off like threads and unravel downstream, feeding the surrounding belt. Monitoring across decades shows that the average rotation period of the storm can vary slightly as its size changes, as if a spinning dancer adjusted speed with a shift in posture. Even as it narrows, it remains a landmark. The reason for its longevity likely lies in the environment that cradles it. The nearby jets offer energy and protective shear. The lack of solid surfaces means no mountain ranges interrupt the flow. Heat from below steadies convection patterns that help sustain the vortex's structure. Altitude brings chemistry that sets its tone. The planet's rapid rotation keeps the Coriolis effect strong enough to enforce circular motion. Each factor contributes without drama. Together, they allow a weather system to live through generations of watchers. There is no need to amplify this into myth. The fact that a storm can survive so long, adapting slowly while preserving identity, is quiet resilience. It offers a human parallel without effort. A person can hold a shape across decades, not by resisting every change, but by making room for small adjustments that preserve the core. The Great Red Spot does not claim the entire hemisphere. Other ovals spin nearby. Waves parade through adjacent belts. On occasion, interactions are close and active. Yet the large vortex remains itself. It serves as a calibration point in the mind's map, a familiar harbor on a moving sea. Instruments have even traced subtle fluctuations in its color and brightness, tied to seasonal shifts in sunlight at that latitude, modulated by the planet's tilt and distance from the sunday. These variations do not command the storm, they tint it. Episodes of narrowing sometimes accompany outbreaks in nearby belts, as if the energy budgets of the region keep accounts. The storm answers the balance sheet by borrowing momentum when it must, and paying it back when it can. The eye of the vortex is not calm in the terrestrial sense. Winds blow there too, though arranged differently, with vertical motion and smaller eddies nested within. Temperature contrasts across the structure shape, which cloud species dominate at various heights. The topmost deck often shows fine streaks wrapped tightly around the oval, traces of the flow's curvature. All of this can be watched without needing to resolve every detail. The assurance that patterns persist and that change can be measured slowly is enough for rest. If the ear asks for a soft image, imagine a woven ring that adjusts its loops yet stays whole. Then let the line fade and keep the facts. The storm exists because physics invites it, and it stays because the invitation remains open. When attention lifts from the long-lived to the brief, the same atmosphere holds shorter sparks that answer a different kind of energy, sudden and sharp, yet tamed by scale. Deep within the cloud layers, towers rise where water condenses and releases latent heat, driving updrafts that break through surrounding stability. In those mixed regions, particles of ice and liquid collide and separate, sorting electrical charge between different sizes and phases. The outcome is a field strong enough to puncture the air and send a discharge across a narrow path. Observers do not simply watch with eyes. Radio instruments catch quick emissions from these events, and cameras tuned to certain wavelengths record flashes that brighten nearby clouds for the briefest instant. These signals occur at varied latitudes, though certain belts and zones seem to favor activity for long intervals, as if conditions there repeatedly meet the triggers for deep convection. The materials involved can be unusual compared with Earth's storms. Ammonia interacts with water under frigid pressures to form slushy particles that can transport charge while falling and rising, transferring imbalance through the cloud. Such mixed hail, tumbling in updrafts, becomes a shuttle for electrons. The vertical reach of some storms is impressive for a gaseous world. Columns can extend across layers where different cloud types dominate, linking liquid water, aqueous ammonia, and ammonia ice in stacked stages. When a discharge forms, the path glows for a heartbeat, revealing structures within the tower that otherwise remain hidden. Spacecraft flying past have mapped clusters of strokes and found that some regions pulse with repeated activity over many rotations, not because the day drives it, but because flow patterns and temperature profiles in that neighborhood keep resetting the stage. Flashes do not transform the planet's night to day. Most are too deep and too brief for that. But their tally accumulates into a clear picture. Electrical weather belongs to Jupiter as surely as the bands do. These events carry energy upward and redistribute heat, helping the atmosphere reach balances set by radiation and convection. Over storm alleys, winds shear cloud tops into anvils. The edges wearing that shear can roll into waves, and trailing plumes trace downstream as markers. In the infrared, warm holes appear amid these complexes, where the cloud deck thins beneath active towers. Microwave measurements reveal columns of altered composition beneath active regions, showing that updrafts dredge material from deeper levels into layers closer to space. The presence of lightning implies deep water abundance sufficient to fuel such convection, a clue used to estimate how much oxygen the planet contains overall. In this way, a flash becomes more than spectacle. It becomes data about the interior's makeup. Compared with Earth, the context differs. Our storms are tied to continents, oceans, and seasons. On Jupiter, the drivers are internal heat and the interplay of jets, with latitude patterns stronger than any dawn or dusk effect. Because the planet rotates so quickly, storms must navigate a field of strong Coriolis deflection, which encourages organization along the bands. Yet, within those constraints, surprises abound. Clusters can merge, decay, or split, their behavior sensitive to small changes in shear and moisture. Some convective outbreaks begin quietly in microwave maps before visible clouds thicken. Others announce themselves with bright tops that instruments catch first in the near infrared. In all cases, lightning serves as a truth marker. Charge separation has succeeded and deep processes are at work. The emotional tether to human experience is simple. Sudden thoughts can appear even in a calm mind. They strike without malice and vanish quickly, leaving a rearranged feeling behind. Jupiter's flashes are like that, short and decisive, but absorbed by a larger quiet. No part of the system panics. The belts continue their lanes. The jets hold their shape. A bolt makes no permanent scar at this scale. It simply moves energy the way it must. For moments, listeners may imagine the inside of a cloud lit by a narrow vein of brightness, like a seam of quick fire opening and closing. The picture helps, then dissolves, and the facts remain. Detectors note stroke rates and locations. Maps update. Circulation models digest the evidence. The next tower rises somewhere along a boundary, and the cycle repeats. All of this happens under a cover of familiar stripes, the same framework that led us from mass to motion, and from motion to the organized weather that carries both age and change. And as the listener's breath slows, the narrative has reached the edge of a different realm of energy, where currents run not only in air but in the deep that conducts, guiding space around the planet into a shape drawn by rotation and charge, a shape that waits quietly beyond the clouds. Beneath the calm stripes and the measured whirl of the day, matter learns new manners and keeps them. Hydrogen, simple as breath at Earth's surface, is pressed until its electrons begin to roam freely, so a fluid that once resisted current starts to conduct. This change does not arrive all at once. It spreads across a deep interior band where pressure and temperature cooperate. At those depths, molecules crowd and dissociate. Atoms share space like courteous travelers on a narrow platform, and the shared crowding creates a state that resembles a quiet metal. Motion persists there, not the frantic kind of boiling, but broad, rolling flows, drawn by buoyancy, rotation, and gradients of composition. Those flows act as a dynamo. They take kinetic energy and turn it into magnetism, arranging field lines that will, far above, carve a vast architecture in space. The metallic region is not a thin skin, nor does it swallow the entire globe. It occupies a middle kingdom, shaped by the cooling history of the planet and by how hydrogen's properties change with pressure. Above it, molecular layers and familiar cloud chemistry. Below it, a domain where heavy elements may concentrate, not as a crisp stone but as a diffuse enrichment that fades gradually into the conductor. Helium, generally at ease with hydrogen, becomes less soluble under certain combinations of pressure and heat. Minute droplets separate from the mix and drizzle downward. That slow rain turns gravitational potential into warmth, a subtle source that helps explain why the planet emits more energy than it receives from sunlight. No fire is needed. The fall itself pays out heat. The presence of this rain changes the local composition, and that, in turn, affects how efficiently the fluid carries heat. Where helium leaves, hydrogen becomes more dominant. Where droplets gather, the mix shifts again. The interior is therefore layered not by rock strata, but by physics, by what dissolves in what, and by how moving mixtures trade places over long times. Gravity measurements taken during close flybys register tiny imbalances in mass distribution that only a complex interior can create. Tracking data sharpen into maps of how density must vary with radius and latitude. Those maps favor scenarios with a diluted core, heavy elements stirred outward by early turbulence or by long convection that eroded sharp borders. Laboratory work supports this picture from the other side. Samples of hydrogen and helium are shocked, squeezed, and heated to conditions that push them toward planetary states. Their responses, how compressible they are, how their phases change, how easily electrons move, feed equations that convert pressure and temperature into density and conductivity. Spacecraft constrain the totals. Laboratories provide the rules. Theory ties both together. The result is an interior portrait that has grown clearer decade by decade, without losing its essential gentleness. No jagged mountains beneath the clouds, only pressure rising, chemistry shifting, and fluids learning to conduct. Heat travels outward through this arrangement by convection and radiation, but convection dominates where gradients become unstable. Warm parcels rise, cooler parcels sink. Rotation steers these motions into columns aligned with the axis, because in a rapidly turning world, flows find it easiest to slide along directions that keep planetary vorticity intact. The metallic layer obeys that preference, so currents loop in tall, slow cylinders that span deep distances. Within those rotating columns, electrical currents generate magnetic fields that add, cancel, and skew. The final field that emerges at the cloud tops bears the signature of those interior paths. Strong, uneven, and just misaligned enough to be interesting. Above the metallic sea, molecular hydrogen behaves more like a familiar gas. Ammonia and water condense where temperatures permit, making the stacked cloud decks that paint the planet's face. But the weather's persistence owes much to what happens deeper down. A steady internal heat flux, compensated by slow cooling across billions of years, supports tower-building convection and supplies energy to the jets. Day and night play less of a role here than they do on worlds with thin atmospheres. A person can think of a house with warm floors. The radiators may be silent, but the rooms stay even. Jupiter's floors are hot by memory. The memory is long. Formation trapped heat when gravity did the initial work of gathering gas. Helium rain repays a portion of stored energy as droplets descend. Slow chemical and phase changes release or absorb heat according to the path the mixture takes. The combination writes a thermal profile that resists sudden change. Because the metallic region conducts, movements there also feel magnetic forces. Those forces, in turn, react on the flows, guiding them in patterns that can sustain or complicate the dynamo's vigor. Seasonal effects, which matter for thin atmospheres on tilted rocky worlds, barely touch this deep drumbeat. Sunlight modulates the color of high clouds. The interior answers to pressure and time. The emotional note that accompanies such a system is patience. Interiors do not confess quickly. Each mission returns with a few more constraints. A slight adjustment to gravity harmonics, a tighter bound on how deep the jets extend, a sharper estimate of the electrical conductivity of certain layers. Each laboratory study adds another point on a curve that used to be sketchy. Confidence builds not from a single revelation, but from many small agreements. This is the kind of knowledge that sleeps well. No rush, no drama, just the slow narrowing of what could be true. Imagine, briefly, a bell with no air to carry sound, only pressure to carry motion. When currents move inside the metallic sea, that bell would ring in a language of magnetism, not music. Then let the image pass. The facts are enough. Hydrogen is transformed by weight. Helium sometimes separates and falls. Heavy elements blur boundaries. Currents generate fields. Heat rises with memory. The surface shows none of this, yet everything above is shaped by it. As the mind settles with that idea, another realm approaches, not the hidden, but the spacious. The place where those inner currents spread their influence outward and sculpt the space around the planet into a living structure that stretches away from the sun and curls back like a long, invisible wake. The space around the planet is not empty. It is organized by lines of force that loop, open, and reconnect. Close to the equator, these lines wrap around the world and form traps for charged particles. Electrons and ions spiral, bounce between converging mirror points, and drift slowly around the planet, building radiation belts that endure. The energies in those belts are high enough to trouble electronics, so explorers that enter this realm prepare with shielding and careful paths. Closer to the poles, lines widen and dip toward the atmosphere, making highways for particles to descend. Farther still, the solar wind presses on the sunward side, compressing the boundary into a blunt bow. On the night side, the field stretches into a tail that runs for tens of millions of kilometers, a structure so long it shares space with distant orbits and responds to gusts in the wind like a banner does to weather. The magnetosphere breathes. When the solar wind strengthens, the dayside boundary moves inward. When it relaxes, the boundary drifts outward. Meanwhile, material from a volcanic moon loads the system with fresh plasma. That plasma is not content to sit. The planet rotates quickly, and the magnetic field tries to enforce co-rotation. At greater distances, plasma lags, and the mismatch drives electric fields that accelerate particles and set up currents. A disk-like current sheet forms near the equator, thick and dynamic, part of a circuit that couples deep interior motion to space. Within this sheet, particles are heated and accelerated. Waves propagate and scatter them, and the overall structure thickens or thins depending on supply and solar conditions. The strength of the magnetic field at the cloud tops is several times Earth's, a sign of robust dynamo action below. Yet the field is not a simple bar magnet. Mapping has revealed patches of intense flux and asymmetries that show the generator is complex, possibly involving flow patterns that differ between hemispheres or with depth. Those irregularities matter. They guide where radiation belts are densest, where auroral arcs brighten, and where spacecraft must pass quickly to avoid prolonged exposure. Instruments reading radio emissions catch periodic signals tied to the rotation of the deep field. These signals act as a clock that does not drift with cloud winds. The clock confirms that, beneath the moving atmosphere, the deep engine spins on schedule. Radio bursts also flare when certain conditions align, giving real-time hints of who is interacting with whom within the system. Ultraviolet and infrared images add their evidence by watching rings of light near the poles brighten and fade. Those lights trace where particles fall into the atmosphere and where magnetic field lines connect to space or to moons. Electric currents flow along those lines, connecting the planet to its environment. Magnetic reconnection occurs in the tail, when field lines from the two lobes are pushed together and break, forming new connections and hurling plasma down the tail. Such events release energy and reorganize the structure for a time before conditions settle again. It is all orderly in its way, not predictable to the minute, but faithful to rules that repeat. A person can imagine an invisible canopy stretched tight and then relaxed, its frame held by the field. The canopy bends and returns. The structure is resilient because it has space to yield. This is vigilance without alarm, a system that looks after itself by rearranging pathways for energy when they jam. A notable feature is the way rotating field lines sweep past orbiting moons. Where a moon contributes plasma, as one volcanic neighbor does relentlessly, the flow builds a torus of ions in that orbit. The co-rotation enforcement then becomes work. Particles must be accelerated to keep pace with the planet's spin. That work draws energy from the rotation and feeds the currents that lace the system. It is a neat circuit. Interior motions build the field. The field organizes the space. Moons load it with matter, and the whole structure responds with currents, accelerations, and light. The harshness here has a kind purpose for science. High fluxes and strong fields make signatures clean. Detectors see clear patterns of pitch angle distributions, of mirror points, of wave-particle interactions. Theory, tested on Earth's gentler field, finds bold confirmations or instructive exceptions in this amplified arena. Engineers learn too. Hardware that survives here will work almost anywhere else. Emotionally, the realm invites respect, not fear. It is like walking beneath a network of quiet bridges, each carrying traffic that never clatters. One feels small, but also safe within rules that rarely break. And as those rules guide thoughts along the field lines toward the poles, the eye meets light that writes the same physics onto the sky. Steady scrolls that rarely extinguish, maintained by constant rotation and sustained supply, a diary that glows while the world sleeps. Around each pole, an oval of emission circles the darkness and keeps its promise. Charged particles, guided by the magnetic field, stream into the upper atmosphere and collide with molecules that respond by giving off light, especially in ultraviolet and infrared. The arcs shift, ripple, and bead with knots of brightness, but they endure. They do not need a clear night or a geomagnetic storm to wake. They remain because the engine that feeds them is internal as well as external. The solar wind modulates the show by pressing and tugging, but the steady rotation of the field and the constant loading of plasma from a volcanic neighbor provide power even when the wind is calm. In that neighbor's orbit, ions and electrons gather into a torus. Field lines that thread that region pick up the burden and tug it along. Potentials form as the field enforces rotation. Electrons gain energy and precipitate along connected lines. Where they enter the atmosphere, a distinct spot flares the footprint of the moon, bright, offset, and tracking its motion like a minute hand. Other moons mark the auroras too, though more quietly. One leaves a subtler trace, influenced by a conductive ocean that alters the magnetic handshake. Another brings the complexity of its own small field, so its signature is modulated by two magnetic personalities meeting. Meanwhile, the main ovals mark where precipitation is continuous. Inside them, The polar caps often show open field line emissions, chaotic and responsive to the wind's changing angle. These lights heat the upper atmosphere. Temperatures there rise above what sunlight alone would predict, a sign that energy is being deposited by particles and redistributed by waves. Spectrographs read the emissions line by line, revealing which species are excited and how fast they move. Some lines come from molecular hydrogen, others from charged variants, each telling part of the story about density, chemistry, and energy input. Over hours, the ovals breathe with the planet's rotation. Bright patches walk along, sometimes fixed in the frame of a moon's position, sometimes free, driven by global dynamics. Over days, the pattern responds to the wind, tightening when pressure increases, relaxing when it fades. Over months and years, small shifts in average position map asymmetries in the field itself, providing clues about how the dynamo has changed or where its flows may lean. Spacecraft have flown through the acceleration regions and recorded electric fields strong enough to explain the electron's energies. The data show that these fields are not steady rods of power. They pulse and flicker, corrugating along the field lines. The atmosphere answers in kind, glowing brighter where currents thicken. The coupling is intimate. Currents close through the ionosphere, and the closing creates drag on the rotating field, taking a tiny toll on the planetary spin, a tax paid in light. Ground-based observatories, viewing in ultraviolet with the help of instruments above the atmosphere, map the ovals and watch for footprints. Infrared telescopes measure heat in the auroral zones and detect hot hydrogen that proves energy has been poured in. The consistency of these signatures sets this world apart from Earth, where auroras arrive under certain conditions and depart when the wind is quiet. Here, the page is almost never blank. Emotionally, the effect is companionship. The lights are not a rare guest. They are a resident. They are a journal written in their own script, adding entries every rotation. A person reading that journal feels steadied by its regularity. The entries differ, but the handwriting remains the same. For a single soft picture, the lights stitch patterns into a dark fabric, each stitch a collision, each line a path traced by a particle that traveled far to end gently. Then leave the picture and keep the facts. Precipitation heats, footprints track moons, ovals encircle, caps wander, currents close. The system teaches by repeating. As attention eases outward from the poles toward the equator, another delicate structure appears. Not luminous in itself, but perfect for backlight. Planes of dust, thin and persistent, sustained not by strength, but by balance, holding their places, like pages laid flat between the weather above and the moons beyond. Near the equator of the giant world, planes of dust circle with patient discipline, so thin that a single glance can miss them. A main ribbon lies close to the planet, bordered inside by a diffuse halo and flanked outward by two broader veils, long known as gossamer rings. The material is not blocks of bright ice. It is mainly grains, smaller than a hair's width, lifted when fast. Micrometeoroids strike inner moons and knock fragments into orbit. Those fragments begin as sprayed ejecta and quickly sort into populations by size and charge. The smallest feel sunlight strongly and scatter light forward, making the system brightest when seen at high phase angles. Larger grains reflect more gently and fade sooner from view. All drift within a balance set by gravity, radiation, and electromagnetic forces, writing a structure that looks delicate yet persists over long times. The main ribbon sits near the orbits of Adrastea and Metis. Both moons contribute debris and help set the ring's inner edge by simply sharing the neighborhood. Their gravity gently prunes the population, letting fragments that wander too near be removed. Beyond the main ribbon, two wide veils carry the names of Amalthea and Thebe. Their dust sheets hang farther from the planet and stretch in fainter curtains that reach across tens of thousands of kilometers. Observers first saw the system as a sharp line when the ring plane turned edge-on and sunlight skimmed the structure. Later, images taken with the sun behind the planet revealed a brighter, textured sweep that confirmed just how strongly tiny grains prefer to send light forward. Particle lifetimes are short. Sunlight drives a slow in-spiral known as pointing Robertson drag, bleeding orbital energy and drawing grains inward. Charged dust interacts with the rotating magnetic field and with the equatorial plasma sheet, changing inclinations, creating the halo's thickness, and shuttling some grains to paths that intersect source moons again. Micrometeoroid flux replaces what is lost. Impacts on Adrastea, Metis, Amalthea, and Thebe throw fresh material into space. The balance among loss, lift, and recycling holds the system present without building mass. Because the grains are small, they feel forces that ignore intuition, born from stones and planets. Electric fields near the planet can loft particles above and below the plane, giving the halo its diffuse thickness. Radiation pressure shifts orbits by tiny amounts that matter over many turns. Collisions among grains redistribute energy and can grind fragments down, feeding the population of the smallest sizes. Spacecraft have refined this portrait. Two early flybys revealed the existence and basic layout. Later missions imaged backlit crescents that exaggerated the forward scattering surge from tiny grains, confirming how dominant the smallest sizes are. Star occultations measured narrow features, linking the main ribbon to embedded source moons. High-phase images displayed the halo as an extended glow reaching toward the planet, shaped by Lorentz forces in the inner magnetosphere. Recent cameras have watched the gossamer veils change brightness with geometry in ways that match models of dust released from the larger inner moons. The system teaches gentle lessons about small forces accumulating over time. Solar radiation, usually treated as light and warmth, becomes a mechanical hand at particle scale. Electromagnetic effects, familiar in laboratory sparks, shape orbits when grains carry charges measured in elementary units. Gravity shepherds without speeches. The small moons simply occupy paths that trim the excess and reseed the plane. Every process speaks softly, yet the outcome is visible across a planet's breadth. The emotional note is tenderness that is not fragile. The rings endure because many weak influences find a shared balance. Observations benefit from geometry. When the sun lies almost behind the planet, forward scattering brightens the rings and reveals structure in the gossamer veils. When the ring plane tilts edge-on to the observer, the main ribbon sharpens to a line, while the halo rises as a dim envelope. At lower phase angles, reflection decreases, and the system fades until only the densest portion remains measurable. These changes teach which particles dominate. Larger grains reflect more strongly at moderate angles. Smaller ones vanish until the backlight returns. Measurements at different wavelengths add another piece. Colors lean dark and neutral, aligning with rocky, space-weathered material rather than clean ice. No solid surface bounds the inner edge. Instead, atmospheric drag and electromagnetic forces prevent dust from thriving too close to the cloud tops. Grains that wander inward either disintegrate, spiral down, or are flung onto paths that exit the plane. The halo's brightness near the planet marks where this struggle plays out. Energetic electrons in the inner magnetosphere can charge dust quickly and drive vertical motion, lifting particles out of the main sheet before they are lost. Such paths explain the halo's thickness and why it glows most with backlighting. The faintness of the entire system is not a flaw, it is the signature of an ongoing process. Collisions on small moons lift dust. Grains evolve under gentle forces. The largest fragments fall back or collide and break. The smallest simply leave, drifting inward until they cease to orbit. Between these ends lies the brief span when grains contribute to the structure that instruments can catch. Human eyes respond to delicacy. The idea that something so slight can keep its place between weather and moons invites ease. The rings neither compete with storms nor with auroras. They share the equatorial sky and ask for favorable lighting, nothing more. Through that patience, they become reliable company. An evening spent with a small telescope can find them under the right geometry. A spacecraft image can return their ends. Thin correction to the idea that only large features matter. The rings say otherwise. Small things working together leave a trace as grand as any single statement. Color and reflectance hint at composition. The system is dark, with tones matching rocky fragments rather than clean ice. That tint agrees with the source moons, whose surfaces are dim and likely rich in silicates weathered by radiation. Photometry across wavelengths shows the strongest signal from tiny grains at very high phase, consistent with rough, micron-scale particles that scatter light forward. The overall opacity remains extremely low, yet across a planet's span, the sum becomes visible. Azimuthal structure appears where ejecta launch from favored longitudes and where resonant motions slightly prefer certain paths. Small enhancements form and fade as collisions and charging tweak orbits over weeks. Unseen moonlets may add local bumps that drift with orbital motion, leaving faint arcs that recur in close observations. These patterns are subtle from far away, but nearby flybys reveal them as quiet proof that even a thin ring carries weather of its own adjustments, rebalancings, and a steady tendency toward equilibrium. As brightness thins, attention turns outward to a restless moon now feeding the system. A small world circles close to the giant and flexes with every lap. Its path is kept slightly stretched by a precise rhythm with two neighbors, so distance and tidal pull change predictably. Friction inside turns that periodic strain into heat. Rock warms, parts melt, pressure finds fractures, and material ascends. Eruptions follow. Some are steady, feeding lakes that overturn. Others arrive as brief surges that lay fresh sheets across older plains. The result is a surface that rarely settles. Maps made years apart do not match in many details, yet the framework holds. A globe remade by tides, not by plates, with vents that return to favored sites, and a circulation of frost that writes seasons in light tones and shadowed fans. The styles of activity are varied but consistent. Broad paterae host lava lakes that circulate and crust. Roofs break, interiors brighten, and cooling skins sink to repeat. Fissures open for distances that can be mapped from orbit, pouring incandescent flows. Certain sources launch plumes that rise high before gravity bends them back. Particles sort by size. Fine grains arc far and coat the countryside in pale mantles. Heavier clumps fall sooner and build rings around the vents. Some plumes appear where hot gas meets frosts and flashes them into vapor that lifts ash and crystals. Others issue straight from vents with velocity set by expanding gases over magma. Each style leaves distinct patterns that instruments can recognize on later passes. Heat distribution within the interior is uneven. Tides dissipate energy most where strain can be moved, and resisted deeper rock and partially molten zones that transmit stress like slow waves. A resonant chain with Europa and Ganymede maintains the needed elongation. Their periods fit a simple ratio that repeats alignments and preserves eccentricity. Without that choreography, the track would circularize, flexing would fade, and the world would quiet. With it, tides remain effective, and the tides keep the ovens lit. Above the ground, a thin atmosphere forms and collapses each day. Sunlight warms frosts and lavas and lifts sulfur dioxide. After sunset, cold dominates, and much of the gas condenses back to the surface. Pressure stays tiny, yet local winds exist. Vents push gas outward. Frosts sublime and migrate. Shadows preserve deposits longer. These motions leave bright fans that point downwind and dark lanes where warmth lingers. Ultraviolet light breaks molecules and starts chains of reactions that paint surfaces with fresh coatings and seed space near the orbit with fragments. Interaction with the magnetic environment threads through everything. Escaping molecules form a neutral cloud around the orbit. Many are soon ionized by sunlight or by impacts with energetic particles. Ions then join the rotating population in equatorial space. Acceleration is required to keep pace with the field, so electric potentials form along connected paths. Energy flows into the plasma and out of it again as currents close through the giant's upper atmosphere. Waves propagate along the connections and return signals that instruments can read, confirming the strength and geometry of the coupling. Measured lava temperatures match hot silicate compositions. Some readings hint at especially high temperatures, consistent with magnesium-rich lavas, though interpretations depend on how rough surfaces radiate and how long they are exposed. Regardless of exact composition, the global power output is clear. Averaged over time, the heat exceeds what radioactive decay could provide in a small body by wide margins. Tidal dissipation must supply the difference. That power emerges unevenly as episodes tap different reservoirs. Some regions stay warm for years, others flare and sleep. In every case, energy drawn from orbital motion is returned to space as thermal radiation, and the cycle continues. The crust responds with blocks and benches rather than organized plates. Mountains stand in sharp relief beside depressions where emptied chambers let roofs subside. Faults step the ground in terraces. Bright aprons lie at the bases of scarps where frosts accumulate in cooler air. Flows pour across plains, halt at low walls, then wait until the next episode buries them. Comparison of images taken a few years apart shows fresh blankets where dark sheets once lay. The pace is brisk by planetary standards, and the record is layered in colors that trace chemistry, temperature, and age. Daily cycles carve their own marks. At morning, frosts extend widest. By local afternoon, parts shrink as sunlight drives sublimation. In the cold of night, gases return to the surface and paint renewed layers. This breath polishes plains and deepens contrast. Thermal inertia differs between rock and frost, so each evening's cooling repeats with similar rhythms. Warm lavas radiate into space for hours after activity, glowing in infrared views while visible light reveals little. Over weeks, minor shifts move frost margins. Over months, new fans overlay old ones in stacks that instruments can read as a diary. Material also escapes. Near some plumes, tiny grains charge and electric fields accelerate them away. Detectors far from the orbit have measured streams of such grains aligned with the planet's rotation. Analyses of speed and composition point back to volcanic sources. In this way, activity becomes a distributed record, sampled far from the Moon. The neutral cloud along the orbit also feeds regions where particles are energized and guided toward the planet's poles, strengthening specific arcs in the luminous high-latitude displays without repeating earlier details. Observations come from many kinds of sensors. Thermal images tally the power of large hotspots. High-resolution cameras capture silhouettes of plumes at the limb and measure their heights and spreading angles. Spectrometers read gases near vents and follow how sunlight breaks them into fragments. Magnetometers detect how currents shift when fresh mass enters the equatorial flow. Dust counters count passing grains and register their charges. These data converge into models that estimate where heat is generated and how it flows. Radiation hazards near the planet shape how close observers travel and for how long. Trajectories balance risk and return, dipping briefly into hostile zones, then retreating to send data. Despite those limits, repeated visits build a time series rich enough to see cycles. A basin that once showed a single overturning front may later show several moving waves. A vent that slept for a year may wake and build a new fan. Small variations add up to a heartbeat of change. Emotionally, the scene reads as persistent work rather than spectacle. The moon takes a condition it did not choose, continuous flexing, and converts it into forms and temperatures that observers can measure. It shows that steady stress can be turned into structure. That idea offers company to anyone easing toward rest. In quiet rooms, pressure softens when given a path to flow. Here, strain finds lava, frost, plume, and dust. Nothing here is frantic. Even the most powerful bursts answer rules that settle quickly into pattern. The neighborhood notices. Energy deposited into the equatorial plasma can be traced in changing densities. Particles drawn from the orbit brighten distant polar light along guided paths. Dust streams flow outward and cross the routes of travelers. Rings near the equator gather grains shed from moons and redistribute them into plains and halos. None of these responses is dramatic alone. Together, they stand out. A small body shares its work with a giant, and the giant writes that work into its sky. And the cycle continues. Eccentricity stays finite. Tides rise and fall. Heat accumulates and is spent. Conduits clear and close. Surfaces brighten and darken. The map is always in draft, and that draft becomes its most dependable trait. For those listening in a late hour, the dependability can feel like ease. Here is a world that keeps its appointments and renews itself without hurry. Orbit by orbit, it demonstrates how motion can be turned into warmth, and warmth into pattern, returning each scene to quiet glow. It keeps moving, learning a cadence. Beneath Europa's patterned ice, a global sea stays unfrozen, maintained by tidal work that never misses a step. The evidence is not opinion. It is a signal read from how the moon answers the magnetic field of the world it circles. As Europa moves through that larger magnetosphere, a secondary field appears, the kind that conductive layers create when external fields change. The simplest explanation is an ocean mixed with salt, because a saline solution conducts and responds with a measured phase and amplitude. That response matches instruments' expectations for a shell of water beneath the crust, not a patchy puddle, but a world-encircling layer, deep enough to hold volumes greater than all the oceans at home combined. The ice above is not smooth. It carries bands, ridges, and tracts of chaos terrain, where blocks have drifted, rotated, and locked in new places. Such patterns point to partial melting below, and to cycles of freezing that break and refit the surface. The thickness of the ice remains a range rather than a single number, but the working picture allows tens of kilometers for the ocean and several kilometers, sometimes more, for the lid. Exchange between water and shell likely occurs through multiple paths. Warm diapirs may rise like rounded intrusions, delivering brines toward the top. Convection in the ice could shuffle heat and move impurities. Localized pockets might melt and refreeze, transporting salts upward and redistributing stress. In some places, fractures could open and accept ocean spray, then heal when temperatures fall. These processes do not operate loudly. They take the patient rhythm of tides, which flex the moon on an orbital schedule set by resonance with neighbors. That flexing dissipates energy as heat, enough to sustain liquid at depth. The sea floor, if rock lies there, would host chemistry where water meets silicates. Interactions of hot fluids and minerals can produce reduced compounds, the kinds that, when paired with oxidants, support energy-yielding reactions. Those oxidants have plausible sources near the surface, where radiation breaks apart molecules in the scant atmosphere and in frost, leaving reactive fragments that could drift downward along cracks or brine paths. In this way, a circuit forms. Tides make heat. Heat makes circulation. Circulation brings oxidants down and reductants up, and chemistry has a place to proceed. Plumes have been hinted by remote sensing, suggested by momentary enrichments of water vapor, or by disrupted ultraviolet light near the limb. These hints are episodic, debated, and precious. If venting occurs, it offers a route for sampling without drilling. If not, near-surface salts still carry stories of exchange. The surface patterns themselves provide constraints. Double ridges, often symmetric, mark where ice has been forced up along a central line, possibly by repeated opening and closing that brought brines into contact with cold frost. Chaos terrains, with blocks set askew in a finer matrix, suggest large-scale disruption, followed by refreezing. Lineae stretch for hundreds of kilometers, sometimes crossing older features as if nothing could resist the stress field at the time of their creation. Crater counts remain low in some regions, implying younger surfaces where resurfacing resets the clock. Elsewhere, older plains keep fainter marks as archives. Spectral data reveals salts and hydrated materials that fit a story of oceanic influence. Magnesium and sodium compounds, perhaps mixed with sulfates or carbonates, appear in certain bands. Radiation alters these materials over time, so freshly exposed sets differ from weathered ones, helping date relative activity. Temperatures at the surface stay deeply cold, but at depth, pressure, and tidal heating write a different ledger. Conduction cannot move enough energy alone. Mechanical kneading must add power. Models that match the induced field and the heat budget favor an ocean with salinity comparable to terrestrial seas, perhaps layered by density and mixed by tides. One can add a quiet emotional thread without disturbing the science. The idea of a sealed library is fair. Shelves of water kept intact by ice, volumes unopened but present. Hope remains scaled to what observations justify. The claim is not that life exists there. It is that conditions suited for interesting chemistry are plausible, and that energy sources are available. Curiosity is allowed to be calm. Future vehicles will narrow uncertainties. Radar sounders can measure ice thickness and detect pockets of brine. Magnetometers will refine the ocean's depth and salinity by tracking the moon's induced response under different field conditions. Cameras will map fracture families and date their relationships. Spectrometers will distinguish between salts altered by space and salts newly emplaced. Landers, or fly-through samplers, if plumes cooperate, can test for organics and isotopic ratios that speak to seafloor conditions. The connection to human feeling is steady companionship with a possibility rather than a promise. People rest more easily when uncertainty is organized. Here it is. Tidal heating is required and present. A conductive subsurface layer is required and detected. Surface geology requires movement from below and displays it. Exchange mechanisms are required and plausible. Chemistry requires gradients and offers them. Each line supports the next without overstating its role. The moon becomes a quiet prospect, not a stage for spectacle. The knowledge that an ocean hides under patterned ice ties to daily patience. Some stories take years to open. They are worth the time not because they guarantee triumph, but because their pages hold meaning whether read soon or later. In that sense, Europa keeps a respectful pace with attention. It shows what it must show and asks observers to build their case well. If alerts of vapor appear again, they will be checked against geometry, instruments, and background. If not, the seafloor will still conduct its silent interactions. The calm rests on a simple chain. Ice stores stress, tides need, salt conducts, and water waits. Another lantern appears in the mind, not bright, just steady enough to mark the path to the next companion in this family of worlds, one whose voice is deeper, lower, and self-possessed, carrying a field of its own. Ganymede stands apart by holding an internal dynamo within a moon's body. It is larger than a small planet, heavy enough to compress its interior into differentiated layers, and somewhere in that depth, a metallic core moves in ways that sustain a global magnetic field. That field creates a miniature magnetosphere nested inside the giant's larger one, a bubble with its own boundaries, reconnection sites, and auroral ovals. Those ovals do not sit still. They rock in response to the external field's changes. The amount of sway depends on the conductivity of layers between the surface and the core. Observations of that rocking match what one would expect if a salty ocean lies beneath the ice. A layer that alters coupling and resists some motions. Thus, two properties, an intrinsic field and an induced response, speak of a complex interior where metal and water both play roles. The surface confirms a history that once moved faster than it does now. Bright grooved terrains crisscross darker, older plains. Grooves mark extensional tectonics in ice, where the crust was stretched, faulted, and refrozen into ridged bands. Dark regions preserve impact records and older textures. The combination implies episodes when internal heat and stress were high enough to mobilize large tracts. Over time, energy diminished, and the engine slowed. Today, the world holds steady. Dynamic past, stable present. Models of the interior suggest an ocean that does not sit as a single layer. Pressure squeezes water into phases that stack, with sheets of high-pressure ices forming beneath or within liquid layers. Salts alter melting points and conductivities, adjusting where liquid can persist. Above, an ice shell holds the markings we can see. Below, the metallic core carries the motions that feed the field. Between rocky mantles and aqueous layers trade heat and shape the moon's long evolution toward a quiet balance. The atmosphere is an exosphere, far too thin for weather. Oxygen appears in trace amounts, a byproduct of radiation-breaking bonds in surface ice. Molecules knocked from grains hover and escape or settle. No clouds form, no winds sweep plains. Yet in the magnetosphere above, the presence of a field changes everything. Particles encounter a boundary where lines connect to the moon rather than to the planet. Reconnection in this nested environment becomes a laboratory for plasma physics at a scale nowhere else available. Currents thread along lines into the polar regions, and faint auroras glow in response. Not as brilliant as those near the planet's poles, but clear in sensitive instruments. Gravity data from flybys supports differentiation. Small variations in the moon's pull on passing spacecraft combine with shape to reveal a dense center, a rocky and metallic core beneath layers that lower average density. Crater counts span from saturated older terrains to younger, more lightly cratered grooves, offering relative ages that match the notion of tectonic renewal, followed by a long deceleration. Where groove sets intersect, one can read the sequence of events, like layers of handwriting from different years. The lack of tall mountains compared with rocky worlds makes sense under ice tectonics. Flows and relaxations smooth extremes over time. Ganymede therefore serves as a keystone in understanding icy body geology. It shows that moons can host tectonics without plates, that oceans can exist beneath thick shells, and that dynamos can run in bodies smaller than planets if composition and cooling histories align. Its distinct field provides a handle on measurements that would otherwise be ambiguous. By watching how its auroral ovals move under external forcing, one constrains interior conductivity. By mapping the field close to the surface, one infers core size and vigor. By modeling standoff distances and boundary shapes, one learns how the bubble resists or yields to the planet's sweeping field. Emotionally, Ganymede offers steadiness. It is the low note that gives harmony a bass. Nothing about it shouts. It holds records with clarity, not drama. For a short human tie-in, think of a deep instrument in an orchestra. Rarely the melody, always the ground. The moon gives that feeling to the system. It underlines patterns and makes others possible by its sheer composed existence. Its oxygen exosphere remains a whisper. Its grooves remain legible. Its field remains trustworthy. Together, these traits make it a reference point for comparisons. Where Europa displays active exchange and Callisto preserves archives, Ganymede combines memory with a signal and hands both to observers. The nested magnetospheres create boundary layers where particles reflect and drift in ways that can be traced and predicted. Spacecraft that cross these regions add points to maps of reconnection and current closure that repeat with variations, strengthening theory through repetition without monotony. Another soft transition follows from this sense of foundation. Having settled with the moon that carries its own field and has likely hidden seas, the eye travels outward to a world less altered by recent strain, farther from strong radiation and inclined toward patience, an archivist whose pages run long and undisturbed, where comparisons find rest. Out beyond the more worked surfaces, Callisto offers a ledger that was never heavily rewritten. Its face is mottled with craters across many sizes, including enormous, multi-ring structures where impact sent waves through crust and froze those waves in place. Few signs appear of resurfacing by tectonic motion or of widespread cryovolcanism in the late record. The lack of extensive grooves and bands contrasts with the siblings closer in. That difference supports the reading of a gentler engine near the surface, one that never drove large-scale stretches or compressions in recent eons. Composition leans toward a near-equal mixture of rock and ice, giving the body a lower average density than Ganymede, and a gravity accordingly softer. Radiation at this distance from the planet is milder as well, making the environment around the ground less hostile to materials and hypothetical instruments. The atmosphere is barely present. Traces of carbon dioxide have been detected, a whisper that hints at outgassing or surface chemistry, but not a system that could organize weather. This reticence has value. When processes change slowly, markings preserve themselves, and scientists can use those preserved patterns to test ideas about impacts, ejector blankets, aging under radiation, and crater saturation over long spans. Crater counts on Callisto approach saturation in many places, meaning new impacts land on old ones, and the statistics reach a sort of steady state. That situation helps calibrate models applied elsewhere, where resurfacing complicates the counts. The multi-ring basins reveal crustal response to powerful strikes. Concentric features mark where different layers moved and recovered. Their dimensions and shapes constrain the mechanical behavior of icy rock mixtures at the time of impact, letting modelers set bounds on crustal thickness, temperature, and viscosity. Despite the quiet at the surface, interior models allow a subsurface ocean insulated by thick ice and heated by the slow burn of radioactive decay in rock. Evidence includes magnetic signatures consistent with an induced field, like those seen at Europa and Ganymede, though the case is gentler here. If such an ocean exists, It likely sits deeper, beneath a thicker, colder lid, and participates in exchange faintly, if at all, at present. Even a sluggish internal sea would matter for structure, altering how the body responds to tides and to impacts, and changing what we expect for long-term evolution. The color and albedo variations across the surface map, radiation darkening and compositional differences. Darker regions often show where fine material has collected and aged under particle flux, while brighter patches mark fresher ice or frost. The overall palette leans toward grays and browns, tuned by space weather. Unlike the more centrally focused storms and belts on the giant world, Callisto's visual rhythm is granular and steady. It asks for patient eyes, then rewards them with coherent systems of rings, rays, and subdued planes that retain their structure at many scales. Gravity data indicates differentiation that may be incomplete compared with Ganymede's. A fully metallic core seems less certain or smaller. Layers of ice and rock mixtures complicate the picture. The result is a body that keeps an older style of construction, less reorganized, more original. That originality makes it a baseline for comparison. Where tidal heating has driven strong changes in closer moons, here radiogenic heat appears sufficient to govern. Where magnetospheric particles hammer surfaces near the giant, here the hammer strikes lighter blows. Instruments still detect sputtering, chemistry, and change, but at tempos suited to long studies. The emotional tone is endurance without display. The moon holds its archive without turning it into a show. For a single calm image, the shelves here are orderly and undisturbed, labels legible, the room cool. Then the image can step back and leave the facts to hold weight. Multi-ring basins sketch crustal mechanics. Crater statistics test models of bombardment. Darkening rates mark radiation histories. Subtle magnetic responses hint at deep layers. Every line fits into a system that prefers reference over drama. Such a place helps the wider study by reducing variables. If one wants to know how much resurfacing has altered a sibling, one asks what would be there if resurfacing had not intervened. The answer, in outline, sits on Callisto's plains. Comparing ejecta spreads across worlds with different gravities and crustal compositions sharpens equations used to back-calculate impactor sizes. Matching the degrees of darkening under different radiation intensities teaches how quickly surfaces age. Combining all of this with crater counts across multiple bodies yields a more complete history of flux in the outer solar system. Callisto's distance creates another kind of gentleness. The radiation environment near its orbit is friendlier to hardware and materials. That practicality matters for planning measurements that require time in place. Long integrations and low-noise maps benefit from quieter particle backgrounds. The moon thus offers not only information but also a hospitable platform. And still, the night continues with a more extended family objects that do not circle as close companions but run ahead and behind in the giant's solar path, gathered where gravity and orbital motion balance into stable niches that keep company for ages. Along the planet's path around the sun, two wide camps of small bodies keep pace, one preceding and one following at angular distances where gravity and motion balance into rest. These regions, known as the Lagrange points ahead and behind the giant, collect objects whose orbits share the planet's year, yet avoid direct encounters. Stability here is not absolute in the eternal sense, but it is generous on human and geologic scales. A mild tug from the sun is offset by the planet's pull and by the geometry of circular motion, and the result is a broad, slow nest where a rock can circle in step for millions of years. Spectra of these companions show surfaces that are often dark and reddish, their reflectance resembling outer solar system populations rather than the brighter, stony objects nearer the Sunday. That tint points to complex organics and space-weathered material, suggesting that at least part of the population carries memories from far regions before settling into these balanced niches. Diversity exists within the swarms. Some bodies display spectral slopes more subdued, some show signs of collisional families, and a few binaries reveal paired histories that survived long marches of time. Missions now travel toward them to untangle this mixture with close scrutiny, because each surface preserves chemistry from eras when disks of gas and dust were drawing planets together. If giant worlds once drifted inward and outward before anchoring in their present lanes, such migrations would have swept, trapped, and reshuffled small bodies. The Trojans, still running in place beside the planet, can preserve the evidence of that migration in mineralogy and shapes. Inside the asteroid belt between Mars and the giant, a different sign of the planet's influence appears as quiet voids in the distribution of semi-major axes. These are gaps where mean motion resonances with the planet encourage chaos in orbits. When a minor body circles the Sun in a time that forms a simple ratio with the giant's period, the repeated gravitational tugs at nearly the same orbital phase compound small changes into large excursions. Over long spans, those orbits empty more readily than neighboring ones. The belt's population thus shows troughs at specific locations, the enduring marks of rhythm applied from afar. Near these gaps, surface processes follow the same laws as elsewhere. Fragments collide, spin states change, and thermal forces like the gentle emission-driven drift in semi-major axis can slowly slide small asteroids into resonance, after which planetary gravity completes the extraction. In this way, bodies feed the near-Earth population or exit to paths that remove them from easy observation. The pattern is not violence. It is order imposed by repeated timing, a metronome that thins certain shelves while others remain stocked. Farther out, beyond the belt, icy visitors approach on long, stretched paths from distant reservoirs. Some pass quietly and leave, their long periods barely touched. Others are detoured by the giant's field, a nudge here, a borrowed energy change there, until their periods shorten into years that bring them close, again and again. These become members of a family of comets whose cycles are short on celestial scales, their roots turned by one heavy presence more than by all other planets combined. The same machinery that sculpts the belt clears or populates these cometary tracks. Close passages inside the giant's sphere of control exchange velocity for redirection. A comet can be promoted inward, demoted outward, or held in a loop that returns it near the giant for many circuits. Over time, sublimation reshapes such bodies, and dust shed along their paths writes thin streams that may later cross a planet's orbit as meteor showers. The chain of cause feels large, yet it rests on steady repetitions of orbital geometry, not on singular events. Influence here is patient guidance, not sudden decree. The Trojans themselves are not a monolith. Their distributions in inclination and eccentricity show that the stable regions are wide and nuanced. Objects oscillate gently around the centers of the Lagrange zones, executing slow loops called tadpole orbits when viewed in a co-rotating frame. Some wander more broadly in horseshoe patterns that skirt the edge between the two camps. Collisions among Trojans occur, though at lower relative speeds on average than in the belt, producing families whose fragments share orbital elements and surface traits. The sizes range from handfuls of kilometers to giants among small bodies. Shapes are often irregular, testimony to low gravity and long collisional histories. Surface temperatures remain cold, so ices may persist beneath weathered skins. Telescopic observations find absorption features that hint at varied compositions, some perhaps containing hydrated minerals introduced by past processing. These worlds rarely come close to the planet, despite sharing its path. Geometry keeps them distant enough for spacecraft to plan smooth flybys and for the gravitational dance to continue undisturbed. Beyond the Trojans and the Belt, the planet's reach is felt in subtle patterns among centaurs, icy, rocky bodies that roam between the giant worlds. Dynamical models show that many centaurs are temporary, their orbits perturbed into new configurations on million-year timescales by encounters with the giants. Some become short-period comets, some are ejected, and some settle for a while in resonances that delay change. In these pathways, the planet plays an editor's role, altering trajectories without erasing histories. A particle's initial conditions still matter. The world's field simply makes certain chapters more likely to be written than others. Evidence for such editing appears in the distribution of inclinations and in the alignment of long axes of orbits that resonate quietly with the planet's period. Closer toward the Sun, in the belt's depths, the locations of other resonances reveal a joint influence of multiple giants. Where the rhythm of one planet coincides with the secular precession induced by another, or where two planets' periods combine into higher-order commensurabilities, regions become inhospitable for long-term residents. The belt's present architecture, with its families, gaps, and gradients, carries the imprint of these layered influences. Observers read that imprint with care, using ancient collisions to back out parent body compositions, and using the dynamic absence of stable real estate to infer the strength of long-lived tugs. Every part of this reading confirms that small bodies are not random scatter. They occupy a map drawn by gravity and time. The planet's role as a shaper extends to dust and faint streams that run along orbits. Particles released by comets or from asteroid surfaces under micrometeoroid bombardment feel radiation pressure that alters their paths subtly. As they evolve, resonances with the giant align some streams and erase others. Rings around the planet itself, though delicate, are echoed by quiet rings around the Sun, formed by many small contributors. Within those heliocentric sheets, resonant trapping can carve diffuse enhancements at specific longitudes relative to the planet, structures that sensitive instruments can detect when geometry aligns. Again, the principle is repetition. Small forces integrated over many circuits produce signatures large enough to see. All of this paints a portrait of guardianship that is not a shield against every stone. The planet diverts, edits, and organizes, rather than simply blocking. Some objects are indeed thrown clear of the inner system after encounters, reducing chances of later impacts. Others are sent inward on new paths. The notion of protection gives way to a truer theme of choreography traffic patterns, established by a massive partner whose steps are predictable and whose influence grows with day. Proximity. That choreography stabilizes many lanes and empties others. It preserves swarms ahead and behind. It thins the main belt at precise rhythms. It recasts distant wanderers into local, repeating visitors. Each effect is measurable, each repeats, and each helps explain why the solar system looks as it does now. For the human ear, the comfort lies in predictability. Guidance does not have to announce itself or make guarantees. Here, it is enough that orbits respond to persistent timing. People find calm in routines that place gentler days beside demanding ones. The giant's routines are cosmic versions of that ease. The swarms that run beside it are still there at each return glance. The gaps in the belt remain thin. Comet families cycle with periods that fit patient calendars. Missions trace arcs through this order to meet small companions whose surfaces remember older suns and colder clouds. A person listening can let those repetitions smooth the late hour. As the mind moves from companions that share the orbit to the wide system, those companions help explain. The sky settles into a final scene, one world turning and influencing without haste, joined by moons, rings, and attendant flocks, all moving in ways that knowledge can follow without strain. Night collects where thought begins to slow, and the giant world becomes a place to rest the eye and trust the rules that made it. Its tilt is slight compared with many planets, so seasons come softly at the tops of clouds. Latitudes receive sunlight in patterns that change only a little through the year, and weather responds more to internal warmth and to latitude than to the date. This steadiness suits late hours. Nothing dramatic insists on attention. Heat from within continues to rise because energy stored during formation and released by deep processes still seeks the sky. Through that steady flow, towers build where water condenses, and jets keep their lanes aligned with latitude, obeying the fast rotation that presses equator and poles into their familiar shapes. Above these patterns, the magnetic field retains a reach that organizes space itself. It draws charged particles into belts, guides others into the atmosphere, and forms a stretched wake behind the planet, where solar wind, pressure, and rotation negotiate positions. The field is not symmetrical, and that asymmetry leaves marks. Some longitudes host thicker radiation. Some arcs of aurora brighten differently. Instruments rate these variations like features of a coastline, returning to them in orbit, after orbit, and finding them reliable enough to serve as landmarks. Around the planet, 4 large moons add their distinct stories. One remakes its surface with heat drawn from tides. Another carries ridges and sealed seas beneath ice. A third holds its own field and retains the geometry of grooves from restless times past. The outermost preserves records with minimal revision. Each belongs to a different chapter of conditions, yet each is bound to the same center by gravity that sets the pace. Smaller moons travel inside the rings, supplying dust when struck by small projectiles and trimming the edges by simply sharing orbits. These arrangements offer chances to test ideas directly. Spacecraft fly by active car. Vents pass through faint rings and thread between magnetic structures. Each flyby refines gravity fields and interior models. Each pass adds to a map of currents and emissions. The process is steady work rather than drama. Patient layers of understanding laid one over another, like quiet coats of paint that deepen a color without changing the scene. Observational history enlarges that calm. Early telescopes recorded the 4 bright moons moving in step, a demonstration of order that challenged older cosmologies. Centuries later, the first dedicated spacecraft raced through the system and returned images of belts, spots, and cratered faces unlike anything known then. An orbiter followed and found lightning where towers reach high, dark fumes at a volcanic rim, and perturbations in paths that revealed mass distributions beneath clouds. Later arrivals mapped the field in detail, measured how deep the jets sink, and tasted the tops of aurora with detectors that count particles one by one. Future craft are already committed to glide past icy shells and through high-latitude curls of light, carrying instruments built to test thickness, sample hawthorns of salts, and listen for the ocean's response when the field outside shifts. These missions follow arcs, chosen to balance hazard and gain, because the belts that glow for physics are stern to electronics. Engineers plan paths that dip into knowledge and rise to safer heights, each loop adding confidence and trimming mystery. The planet's place is not only local. Its mass and location act on wider populations. Families of small bodies in stable positions remain as witnesses to early migrations and captures. Voids in the main belt line up with the timing of the planet's year, showing where gentle resonances become persistent evictions. Visitors from distant reservoirs find their paths adjusted, some returning on short cycles to leave dust and write narrow streams into heliocentric space. Each of these patterns is a handle on processes that would otherwise be abstract. They become threads that tie a human evening to a sky that does not need us but contains our questions easily. A person can fall asleep while a mission coasts through darkness toward a Trojan, while another turns past an icy shell and waits for instruments to wake, while a third watches auroral ovals brighten and fade with the line of sight fixed on a pole. The system continues in that generous way, keeping its appointments whether anyone watches or not. Instruments see more than eyes can. Radio receivers count the planet's rotation by listening to emissions linked to deep currents. Magnetometers feel the tug of the field and write curves that are matched to models of flowing metal beneath the clouds. Cameras sensitive to ultraviolet watch ovals that rarely extinguish. Infrared spectrometers find warm hydrogen in places where particles have poured in. Neutral gas detectors read faint breaths above an icy plain and write numbers that speak of sublimation and collapse with day and night. Gravity science tracks the slight changes in a spacecraft's speed as it flies low, turning those nudges into maps of density and depth. Each dataset fits beside another without crowding. The result does not demand a single headline. It forms a layered picture that supports rest, because it adds weight softly to what was already sure. Late in the day, facts themselves can be calming. The planet's day is short, but repetition makes it gentle. Its tilt is small, so seasons fade and return without sharp edges. Its field is strong, but the rules it follows are clear. Its moons are varied, but each variation fits into a structure that holds. Its rings are faint, but persistence writes them back whenever lighting permits. Its neighborhoods in space include patient swarms and filtered belts, not because someone decided they should, but because gravity and time favor such shapes. For a single soft image to hold, imagine a harbor where buoys align by the tide and vessels pivot on their lines. When wind freshens, the pattern flexes and returns. The scene remains readable and kind. Then let the image release so the details can rest again in factual light. Anyone lying awake can choose any level of this order and find a comfortable scale. It can be the low certainty that a bright point in a small telescope is accompanied by 4 dots that change position nightly in ways a simple chart can predict. It can be the assurance that an auroral oval curves around a pole while the solar wind pressures the boundary inward or outward by small amounts. It can be the knowledge that an ocean hides under a shell and that a magnetic signature gives it away from a distance. It can be the thought that dust is lifted from a moon's surface, circles for a time, and is replaced by the next small strike, neither increasing nor vanishing completely under the management of balance. Or it can be nothing more than the understanding that steady processes can make large structures without fanfare. As breath slows, the mind may walk these levels lightly, from swarms, traveling in step with a world, to voids created by rhythm alone, to strings of light tied to field lines, to a hidden sea that answers to the sweep of an external magnet. With each pass, the tone stays the same. There is no need to decide what matters most. Everything fits. The planet does not rush, does not stall, and does not perform for us. It continues with a firmness that frees attention from worry. It is enough to know that layers hold, that orbits keep their distances, and that energy moves along paths that knowledge can describe. If sleep arrives, it arrives into this order. And if it delays, the order will still be here, quiet, proportioned, and patient. Good night.